Werner's theory of coordination compounds. Alfred Werner in 1898 propounded his theory of coordination compounds, in which he was the first to study the bonding in coordination compounds. And the main points or main postulates of this theory are: in coordination compounds, metals shows two types of linkages, means valencies, primary and secondary valencies. For example, in this example, here this Cl3 means chloride carries -1 charge and 3 chloride carries 3 minus charge, and this is the primary valency, means oxidation state of the cobalt. In this example, it is the oxidation state of the cobalt central metal ion, which is satisfied by the negative ligands, and this shows the primary valency. And the secondary valency is the number of ligands which are directly attached to the central metal atom. Here in this example, 6 ligands are attached to the cobalt atom. 6 amine atoms are amine molecules are attached to the cobalt central metal ion, and this is the secondary valency, or you can say secondary valency is the coordination number. This is the coordination number, and primary valency is the oxidation number. The secondary valencies are non-ionizable. The molecules, the ligands present in the coordination sphere are non-ionizable, means they do not dissociate into the solution. And the primary valencies, these are ionizable. When we dissolve this compound in the solution, then it dissociates into 4 ions, 3 Cl negative ions and 1 this complex CONS363 positive. It means these counter ions, these primary valencies are ionizable. And the next point is the secondary valency is equal to the coordination number, as we have already said that secondary valency is the coordination number and is fixed for the metal. And the next point is the ions or groups bound by the secondary linkages to the metal have characteristic spatial arrangements according to the different coordination numbers, means they form definite geometry with the central metal atom. These are the main points of the main postulates of the coordination, Werner's theory of coordination compounds, in which secondary valency is the coordination number which is non-ionizable, and primary valency is the oxidation number which is ionizable and is satisfied by the negative ions or negative ligands, and secondary valency is satisfied by the neutral molecules or negative ions. Werner performed a reaction between cobalt chloride and ammonia, and he found that it forms a number of coordination compounds. These are the number of coordination compounds which are formed when he performed a reaction between cobalt chloride, a simple salt, and ammonia. And these Cl dotted lines here represents the primary valency and solid lines represents the secondary valency. And the primary valency is satisfied by the negative ligands, that is Cl in this case, and the secondary valency is satisfied by the neutral or negative ligands. Here we have neutral ligands. These are 6 neutral ligands. Ammonia is the neutral ligand. Secondly, when we dissolve this compound, it forms 4 ions. It dissociates into 4 ions. And another compound, like in this, it dissociates into 3 ions because one chlorine is in the coordination sphere, and it dissociates into 3 ions, 2 Cl negative and 1 coordination complex. And in this third structure we have only 2 ions, and in this there is no ionization. And Werner observed from here that when he treat these coordination complexes with excess of AgNO3 solution, only counter ions react with AgNO3 solution and form AgCl in the precipitate form. It means only counter ions participate in the reaction, not the ligands present in the coordination sphere. And this shows that the primary valencies are ionizable and secondary valencies are non-ionizable. Limitations of Werner's theory. It could not explain the why all elements don't form coordination compounds. Only some of the elements form coordination compounds, like transition elements, cobalt, nickel, zinc, etc. And the second is it failed to explain the directional properties of bonds in coordination compounds. Means directional properties like along the axis, how they form the bonds in the coordination compounds. And the third, it does not explain the color and magnetic and optical properties shown by the coordination compounds. In Werner's theory, there is no explanation of magnetic, optical, and color which are exhibited by the coordination compounds. That's why this theory is rejected. Next is valence bond theory, according to which the central metal atom or ion has the required number of vacant orbitals for accommodating the electrons donated by the ligands. It means central metal ion must have vacant orbitals for accommodating the electrons pairs or lone pairs which are donated by the ligands which are directly connected to the central metal ion, and the number of vacant orbitals is equal to the coordination number of the metal ion for a particular complex, and the vacant orbitals may be s, p, d and f orbital. This is the main point of the valence bond theory. Now we will discuss the formation of octahedral, square planar and tetrahedral complexes on the basis of valence bond theory. First of all, we will discuss about the octahedral complexes. Octahedral complexes in which coordination number is 6. It means 6 ligands are attached to the central metal ion. For example, in case of hexaamine chromium, here chromium is the central metal ion. This is the central metal ion, and NH3 amine is the ligand, and 6 shows the coordination number, in which chromium has atomic number 24 and its outer shell electronic configuration is 3d5 4s1, and in here it is plus 3 charge. It means chromium is in plus 3 oxidation state, and here it lost its 3 electrons, one from 4s and 2 from 3d5, and we left with 3d3 electrons, and 4s is empty. Or in the orbital form, it is represented as Cr3 positive, 3d3, 4s is empty, and 4p is also empty. And we have 3 electrons in the 3d orbital, and in the complex we have 6 number of ligands, so we have the central metal ion must have 6 vacant orbitals. Here in this case, these 2d orbitals are vacant, 1s is vacant, and 3p orbitals are vacant, which forms D2sp3 hybridization. The lone pair from 6 ammonia molecules is accommodated in these 6 empty orbitals and forms the hybridization of D2sp3, and the geometry of the compound is octahedral. Next example is the formation of ferricyanide ion FeCN6 3 negative, in which Fe is present in plus 3 oxidation state, and Fe has atomic number of 26. It means it has 3d6 electrons and 4s2 electrons. By losing its 2 electron from 4s and 1 from 3d6, we left with the 3d5 electrons and 4s 0, or it may be represented like this: 4s 0, and this is 4p. Here it is 5 d electrons, and Cn is the strong field ligand. Due to its strong field, it pair up the electrons in the d orbital, 3d orbital, and it becomes like this, and two of the d orbitals become empty. 4s remain empty and 4p remain empty. And the hybridization of this complex is D2sp3. D2sp3, because Cn is a strong field ligand and it pair up the electrons in the 3d orbital and make two orbitals empty to accommodate the 6 lone pairs from the cyano ligand. And the hybridization of the complex is D2sp3 and the geometry of the complex is octahedral. Next example is the formation of ferricyanide ion FeCN6 3 negative, in which Fe is present in plus 3 oxidation state and Fe has atomic number of 26. It means it has 3d6 electrons and 4s2 electrons. By losing its 2 electron from 4s and 1 from 3d6, we left with the 3d5 electrons and 4s 0, or it may be represented like this: 4s 0, and this is 4p. Here it is 5 d electrons, and Cn is the strong field ligand. Due to its strong field, it pair up the electrons in the d orbital, 3d orbital, and it becomes like this, and two of the d orbitals become empty. 4s remain empty and 4p remain empty. And the hybridization of this complex is D2sp3. D2sp3, because Cn is a strong field ligand and it pair up the electrons in the 3d orbital and make two orbitals empty to accommodate the 6 lone pairs from the cyano ligand. And the hybridization of the complex is D2sp3 and the geometry of the complex is octahedral. Next is the formation of COF6 3 negative ion, in which cobalt 27, 3d7, 4s2, and cobalt is present in 3 positive state, and here we left with 3d6 and 4s0 configuration. And in cobalt, in 3d there are 6 electrons, and in 4s there is no electron and 4p is also empty. This is the 6 electrons in the d orbital. Here this is 4d. These are 5 orbitals. Of equal energy. Here this fluorine is weak field ligand. It means it doesn't have any tendency to pair up these 3d electrons. It do not pair up these 3d6 electrons, and this complex, this central metal ion uses the 4d orbitals to accommodate the lone pairs or electrons donated by fluorine, like this. These two d orbitals, 4d orbitals, are used by this cobalt 3 positive, and its hybridization is sp3d2, which is again octahedral complex, but here it uses the outer d orbitals, and that's why it is called as outer orbital complex. Outer orbital complexes are those complexes in which the central metal atom uses Nd orbitals. Here cobalt uses Nd orbitals. N is the principal shell, main shell. And in the complexes in which the central metal atom uses n minus 1 d orbitals are called inner orbital complexes. Uh, for example, FeCN6 2 negative, FeCN6 3 negative, CrNs36 3 positive. All the examples which we have already discussed are the examples of inner orbital complexes. They uses n minus 1 d orbitals, means orbitals penultimate shell, orbitals from the penultimate shell. That's why these are called as the inner orbital complexes. Those uses nd orbitals, outer orbitals, are called outer orbital complexes.